All right. So now we'll be calculating probabilities. We'll look at the fundamentals of computing probabilities. This is going to be the simplest case, where we'll just look at the fundamentals of, and this is more or less like the frequentist approach to probability. And so we need to start with that. I initially didn't want to go into this, but I noticed that when we get to conditional probabilities, we will need some of the notions from here to work with conditional probabilities, which now take us to the Bayesian interpretation of statistics. So now um, I want you to get your pen and paper. If you have them, let's get to work. We're working with a case study here. What I want you to do, instead of starting with presenting formulas and telling you that this is a formula to use in this particular case, let us make it more practical. Okay, let us look at a more serious case study. We'll be looking at the roulette wheel. So the notion of probability really began from, or the need for probability started probably around the 18th century, and it started from gambling. Okay, so which is why we'll be coming back here. So let's say you are in luck and you have millions of dollars. You find yourself in a casino, and so you now need to you want to play to win. Okay, so you're going to be placing a lot of bets here. All right, or even if you don't have millions of dollars, maybe you're lucky. Someone just says, you know what, today's a lucky day. I'm going to be giving you a rack of chips, so feel free to squander them. And if you win, keep all the winnings. If you lose, well, you have lost. You have lost the chance to be rich. Okay, so you find yourself on the table. On that table, you have what are the people in this meeting? Okay, so on that table, you have me, you have Andile, you have Madam Angela, you have Christian, you have Lillian, you have Marian, you have Olawale, and so on. So you have, let's say, all of us right now on the table. Okay, and so we are going to be placing bets. So we'll be using probabilities here, and we'll be starting with the basics. Okay, so are you guys ready? Do you have your pen and paper ready?
Yes.
Okay, anyone else with me?
I'm with you, but I'm on the way. I'm not at all.
Okay, no problem. No problem. So, yeah, you're on the wheel. We're also on the wheel. So, more or less, we are not very different.
Yes, sir.
All right. Now, the roulette wheel is simply someone spins the wheel, okay, spins the ball in the opposite direction, and then you place a bet on where you think the ball will land. Is it not? So, you want to just you're making calculated guesses, okay, and so we want to see how probability helps here, so that you don't make wrong guesses. And there have been cases of people winning in casinos simply by manipulating some of the principles of probability. But with probability, it doesn't necessarily mean you would always have um, what you are computing, okay, or you always have the outcomes that you computed or that you calculated. So that's very important. Always expect that, because it's a probability, not a possibility. There's always going to be a margin of error. So that margin of error could be what could happen to you. All right. Now, in this casino wheel, the pockets, there are pockets in this wheel. Each of these spaces or holes, if I should say, they are pockets. Okay. And so all these pockets are how many in number? You can take a quick glance on this and tell me what you observe as the total number of pockets you have here. Okay, very quickly, the highest number that we have here is 34.
36.
Okay, we have 36. Yes, 36. Okay, that's total number of, that's the highest number that we have there. But that's not the total number of numbers that we have. Okay, the highest number here is 36, but we have more pockets than 36. So how many pockets do we have in total? Anyone noticing that there are pockets, there are two pockets here that are white? Did you notice two pockets here that are white?
39.
Please. and this?
39.
39? Did you count them one by
Yes,
one?
39.
No, I
That's,
think they're more
that's
than
38
39.
now.
It's 38 actually. The highest number here
It's
you
going to
have
be
here
30.
is
Just add the 2
36.
whites plus the
1 to
36.
36. Then simply add the 2 whites, you have 38. Yes, that's very good. 38. You get. Now, the roulette wheel is not really like it's not really black and white like this, okay? So it's just that this is the picture we have here. So the white is like the green. Okay, the actual color of this roulette wheel, this 0 and 00 are green. Okay, the pockets in gray color are actually red color, and then the pockets in black are of course black. So you have three colors on this wheel. Um you have black colored pockets, you have gray colored pockets, I mean you have red colored pockets, and you have green colored pockets. So the whites are green. How many green pockets do we have here?
You have 2.
We have two. How many red pockets? Of course, you have to count that. So, in order not to waste time about that, let's just skip that. Then we have black pockets also. So let's also now get to the details. Now, your challenge is to place all sorts of bets on the wheel. So if your bet falls into any of the white pockets, that is the 0 or the 00, I think it should be green, not white. But let's just leave it as white so that we easily relate to it. So if your bet falls into any of the white pockets, now let me change that to green so that we get used to that. Let me change this to green. Um, stop. Okay. So if the bet falls into any of the green pockets, which is the 0 or the 00, you lose. Okay. Then if it falls into the other pockets, there's something to win there. So now that is our challenge, to place all sorts of bets. Now let's start from the very beginning. Before we go into more advanced betting, let's start um, from a very simple case. Now remember that your probability is encoded as a number between 0 and 1. Okay. Now your outcome. I don't think I noted this. Just give me a second. Let me add this to just a second, guys. All right. So where did we stop? So now we have all these. I hope my mic is on.
Yeah.
Sorry, just give me a sec. Sorry about that. All right. Now, we want to place bets. So your events, okay, your events are any outcome. Which event is any outcome or occurrence that has a probability assigned to it, which means any possible outcome in um, this whole scenario you're dealing with here, okay, any possible outcome with with a probability assigned to it is an event, okay, and then the sample space is a set of all possible outcomes. So there are some outcomes here that are not possible. They are impossible outcomes, so the probability of their occurrence is 0. Let me ask this quick question. What's the probability of finding we say that there are 38 pockets in this roulette wheel, right? Are you with me?
Yes.
Okay, so what's the probability of finding um or of having your ball roll into 38, the pocket 38? What's the probability that your ball will roll into 38?
0.
Why is it 0?
It's 0 because there's
Why?
no
There's no
pockets
38.
in 38.
Yes, there's no pockets 38. So it's an impossible outcome. You already know that this is not an event in this sample space. So this sample space includes all the outcomes that are possible, okay? And each event is any of the possible outcomes. So if the ball enters pocket 34, that's an event. Okay, so the event has two things we're going to be talking about. That event of a ball entering into pocket 34 is going to be dealing with two things or two numbers. What are they?
The outcome and the probability.
Yes, the outcome itself and the probability. So that's each of those events will be dealing with those two things. So what's the total number of possible events that we can have on this roulette wheel?
That's 38.
Yes, there are just 38, what's it called? There are 38 possible outcomes that we can have here. So now, when you're going to be checking the probabilities, we will now be trying to compute, the number of, I mean, the that particular outcome that happened, divided by the total number of outcomes. So let's begin from, I think, okay, let me start by asking some questions. So, um, so remember I said it's going to be very interactive. I don't know how I should do this. Probably, I should use, um, I wish there was a way we could interact, just like in the Jupyter Notebook, uh, um, the Jupyter Notebook collaborative project we did the other day. I wish that was possible here, where we just be working on the same documents, so that each person is contributing to what we are dealing with here. All right. So maybe what I would just do is, I would ask a couple of questions, okay, and then I want each of us to try to answer the questions. So let's start with a simple question. We have this roulette wheel. So just we're trying to build up some of the concepts of probability, but I want to build them up instead of just starting with formulas and showing you expressions and all that. I want to build it up from this case study. I hope that makes sense.
Yes.
All right. So
Yes, it
now
does.
let's start from the base, okay? Trying to compute a simple probability of one of the outcomes occurring. So let's say pocket number 8. How many pockets do we have for pocket 8? How many pockets are there for the number 8? Probably I should,
Just one.
okay.
One.
What I'm going to do now to make this very easy, not this. To make this very easy, I'm going to enlarge that. I'm going to enlarge this. Let me come up this. So I will enlarge the roulette wheel so that we can clearly see it. Okay. So if we come here, we have this. So I heard one. So I guess we can all agree that there's just one pocket we have for the number 8. True or false?
True.
So now I
True.
want to, yes, now I want to calculate the probability that that outcome would occur. So we have that the outcome itself, there's just one outcome that we can have. A ball rolling into 7, okay, there's just one outcome that we can have for that. All right. Now let us try to compute the probability. So what's the probability that a ball will fall into 7? So to get that, we need two things. We need the number of outcomes we can have in this scenario, and we also need the total number of outcomes that are possible in the sample space. That is, this sample space has a set of all possible outcomes. I think so as I was saying, we have a sample space where the total number of outcomes, I hope you guys can hear me. Let me see. Can you hear me?
Yes.
All right. So the total number of outcomes here is 38, right? So the sample space has 38 events. Okay. Now, we are talking about the probability that a ball will roll into the pocket. Is it 8 or 7? We're talking about 8. So
Eight.
we've identified that that event has how many outcomes? how many possible number of outcomes for that event?
Just one.
Just one. So what's the probability that that outcome would occur?
1/38.
Yes,
1/38.
exactly. It's 1/38 because we have just one outcome for that, and the total number of outcomes in the sample space is 38. So the probability that that one outcome would occur in that sample space is 1/38. Okay, so please, if you are with your pen and paper, take note of this because I just want us to be, putting this down so that it kind of sticks faster. All right. Now, what does 1/38 look like? If you say 1/38, you might not really be sure of how small or how big it is. You can just take a quick guess and say, okay, this is really small. But for you to really get the actual value, we have to divide. So when you divide 1/38, we are going to get, let me see, 0.00 what? 1 divided by 38, you get 0.026. All right. So if you draw a scale, maybe a line, like a number line, you can, if you're with your pen and paper, you can draw a number line, start from 0 on the left, 1 at the right. You can demarcate the number line at the middle and put 0.5 there. So 0.5 is like your in-between probability. So from this number line, by scale, you already know that 0.026 will be quite far, far from 0.5, and of course from 1, it will be very close to 0. Okay. So how would you describe the likelihood that you will get an 8? How would you describe the likelihood that you will get an 8? That is when the ball is when the ball lands in 8. What is the likelihood that the ball will land in 8?
It's not so likely to land in it. Like the possibility is very slim.
Yes,
The
the
probability.
probability. Yes, thank you. The probability is very little, so that is a rare event. So it could happen, but it is not so likely. It's so rare. Do you understand? So anyone just being so confident that their ball will land in a specific pocket is joking. Okay, even if it happens, it's just really much of luck. You understand? So the probability is very small. When you draw your number line, it's very close to 0. So this is not a very likely event. It's a rare event. It's not impossible. It's not impossible, but it's not very likely. Okay. Now that doesn't mean that it cannot happen. Okay. So when you're calculating probabilities and you're on this table trying to compute the probabilities, and you are trying to place a bet on the fact that your ball will land in 8, you already know that you are in for a very risky move. Okay, so the uncertainty here is a risk. Okay, I talked about uncertainty versus risk. Now that you are playing this, placing a bet on a particular number now is a risk, because by the time you compute the uncertainty that you are amassing to yourself based on that position that you want to get into 8. Okay, by the time you compute the probability, it is 1/38 or 0.026. So the uncertainty to you at the moment is a risk. I hope that makes sense. Hello, are you guys with me?
Not much, sir.
Yes, sir.
All right. So what we're trying to do here is to build up the principles from scratch. So from what we've computed here, you can simply say that your probability is number of ways of total number of ways of winning, or uh, the number of outcomes for a particular bet divided by the number of possible outcomes in that sample space. So probably I should jot that down here. I wish I was trying to find a way to um, so let me just take note of that here. So you can just take note of this. It's a very simple formula anyway, so it's not something that you probably need to worry too much about. I'm going to put this in equation. So probability for each of the events is, in order not to just use so much of so much of notation. Let me just start with words. So I'm going to put this in. All right. So your probability is simply the number of possible outcomes in the event divided by the total number of possible outcomes in the sample space. So for the events of your ball landing in 8, the number of possible outcomes is what? Is 1. Okay. And so for, let me increase the entire font here. And so for, your probability would then be 1 over 38. So what if we have, more intricate scenarios like maybe trying to place a bet on more interesting things. Okay, trying to check more interesting things. More, maybe a combination of different pockets, so different outcomes for a specific event. The event in this case is a single movement of the ball, okay, landing into a pocket. But the outcome is like the various alternatives based on what you are betting on. All right. So let us look at more scenarios. I think I can put this in notation to make it easy to work with. So let's do this. So we can call this probability of an event E occurring, and we just say here the number of possible outcomes for that event and divided by the number of possible outcomes in that sample space. This is supposed to be E, not A. So the event E divided by the number of elements in the sample space. Let me increase this to full screen so that we are seeing it well. I hope this makes sense. So at the beginning, this is the first formula you're working with. When you are trying to check the probability of an event, what is the number of possible outcomes you can have for that event, divided by the number of possible outcomes you can have in the sample space. I hope that makes sense.
Yes, it does.
Okay. So we are doing much of boring math today, but as we proceed, when we begin to look at probability distributions, of course, our implementations will be in Python. For all these things, we cannot just start implementing them in Python. We have to build the basics. And I don't want to assume prior knowledge. I don't want to assume that we're probably acquainted with this, because that might not be a very good assumption. Okay, so let's come back to our roulette wheel, and let's now try to do some other things like, okay, what if now we want to talk about how do I put this? What if we want to now talk about the probability of not getting an 8? Okay, we have computed the probability of getting a 1. So the number of outcomes for that, for getting a 1, I mean, we've talked about the probability of getting an 8. The number of outcomes for an 8 is 1, and the total number of outcomes possible in that sample space is 38. Now, what if we want to talk about the probability of not getting an 8? How are we going to get that probability? Very quickly, can someone tell me?
Just one.
1 minus probability of getting an 8.
Okay, I can see that you guys are on track. Okay, so you already know that if you can only have a total probability of 1, is it not? So if an event, if you have the probability of getting an outcome, okay, probability of an outcome happening, then the probability of the outcome not happening is simply 1 minus the probability of the outcome happening. True or false?
True.
Okay. Now,
True.
how do we arrive at 1 minus PE? So let's call this let's walk back from here. Okay, so this probability of the event happening, but let's come to the probability of the event not happening. So we're going to denote this with E prime. So E prime is like the complement of E, which means everything in the set outside E. Okay, so everything external to E is your E prime. So which means E prime is simply the probability of E not happening. All right. Now, so what you have here. So the probability of E, the event E not happening, is simply 1, which is total probability, minus probability of E happening. And so in this case, we're talking about the probability of 8 happening, that is probability of your ball landing in 8. And so the probability is P of 8, for example. Then what will be P of 8 prime, which means the probability of that 8 not happening, of your ball not entering into 8, you're going to have 1 minus PE. But I want us to compute that based on this formula. Let's assume for now that we are not aware of this, okay? Because mathematically, for you to even use this formula, you have to prove it. You have to derive. You have to derive this because okay, we have said this. It kind of makes sense, but what is the theoretical justification that actually P of E prime is equal to 1 minus PE? You're going to say, well, if you add P of E plus P of E prime, that's going to give you 1. We need mathematical proof starting from the manipulation of this formula here. So let's start from here, okay? I hope that makes sense. So what's the probability of not getting an 8? Starting from this formula, what's the probability of not having or of not getting an 8?
That's 37 over 38.
Okay, how do you arrive at 37?
1 minus 1 over 8.
You are still
1 minus 1 over 38.
you are still using 1 minus this, okay? So I mean, if I ask you, you said 37 over 38. So how do you figure out the 37? All right, before dividing by 38.
No, I'm
We
giving
take
the
out
driver
Except
the
eight.
money. This is the first time
I didn't get that.
it's done, so
We
I
take
don't know,
out
maybe
the
he
8 from
remits
the
it to you
sample
or something.
space.
Who is talking? I can hear so many voices. Okay, Miriam, go first. Let me hear what you said.
I said take out 8 from the sample space.
We take out 8 from the sample space.
Okay.
Okay, that's a good one. So what happens when we take out 8 from the sample space?
5,000.
It reduces by 1
Okay,
to
you know what you have done?
37.
That's a good one, but you know
9
what you have done?
cartons.
Sorry, who is talking? You know what you've successfully done when you do this? You have successfully still come back. You have come back to this formula here, taking 1 out of the sample space, which is taking that 8 out of the entire whole of 38. All right. It's correct, okay, but not from this perspective in which I want it, but it's still very correct and valid. So what I really want here is what is the number of possible outcomes for event E not happening. That's simply what I'm talking about here. So for event let's go back to the diagram. For this event 8 to happen, where's 8? This is, are you even sure we have 8 on this? Okay, this is 8.
Besides for
Yeah, this is 8. So for event 8 to happen, there's only one 8 on this board, and so it's just one outcome, one possible outcome that will happen here. But for 8 not to happen, okay, for 8 not to happen, there are other, we need to find number of these other possible outcomes. Do you understand? So to find the number of these possible outcomes, we will do a count, of course, that which is 37, but you can then now come back here to now say, okay, 38 minus this. All right, so yeah, Marion, you're still correct. Maybe I should not say you're not correct from this notion. It's still correct. Okay, so we are more or less excluding 8 now from the rest of the sample space. So we find out that there are 37 possible outcomes for 8 not to occur. And so the probability of 8 not occurring is the total number of possible outcomes that 8 will not occur, which is 37, divided by the total number of possible outcomes in the space, which is 38. So that probability is 37 divided by 38. Does that make sense? I hope that makes sense.
Yes.
So in this
Yes.
case now, for this reason, the event E and the event E prime are called complementary events. So these two events are complementary events. So E is complementary to E prime is complementary to E. So everything outside the space, everything outside the possibility of E occurring is complementary to E. And everything outside the possibility of E prime occurring is complementary to E. All right. And so to calculate the probabilities, we simply, working from here, we simply just subtract this probability from 1, because by the time you add the two probabilities together, you're actually getting 1. So since they are complementary events, sorry, can you turn off your mic so that we, please turn off your mics. So we can get the, I mean, we have to now recognize that the summation of the two probabilities gives you 1. Okay, so the probability of one event not happening plus the probability of that event happening, when you add them together, they give you 1. All right, so this is a very important summation, okay, for complementary events. We're going to be needing this for other notions that we'll be working with. Now, let's proceed a little further. Let's say, okay, let me not just start working with that. Let's come back to some other probabilities. Okay, so coming back to the roulette wheel. All right, we already identified some colors, some pockets that we have. We have 2 green pockets, okay, and you've already said that either way, whether it is this 0 or the other 0 0, those 2 green pockets, once your ball enters the green pocket, what happens? You lose. Okay, and so we also have the red pockets and the black pockets. Now, what is the probability of an event? What's the probability that how do I put this? What's the probability of having a successful outcome for your ball entering into the green pocket? That's what's the probability of getting a green or landing in a green pocket. I hope that makes sense.
That's 2/38.
Okay, 2/38. That's a good one. Oh, do we agree with that?
Yes.
All right. Now, what's probability of getting a black, of landing in a black? Now, to make that easy for you, if you count the what's it called? If you count the total number of blacks that you have, all right, you have how many? You have 18 here.
18.
You have 18 blacks here, and then you also have, of course, I think they are actually even numbers of black and reds. I mean, they are equal numbers. You have 18 blacks, 18 reds, and then you have 2 greens. So what's the probability of getting a black?
18 over 38.
Yeah, so you have 18 over 38. Of course, you would either want to convert these probabilities to decimals or reduce them to lowest terms. So for the case of having a green, probability of having a green, you have 2 over 38, which is equivalent to 1 over 19. Is it not?
Yes.
And then for the case of having a black or a red, you have 18 over 38 for both cases. When you reduce that to lowest terms, that gives you 9 over 19. Okay, if you check that, if you compute that, let me see. If you compute or if you divide 19 divided by 38, sorry, 9 divided by 19, you're going to be getting 0.4737 approximately to 4 decimal places. Okay, so the events for a green happening is 1 over 19, which is 0.0526. For black or red, you have 0.4736 or 37. Then what's the probability of getting 39? What's the probability of landing in a 39 pocket? Okay, Messi says 0.
0.
All right. What's probability?
0.
Yes. What's probability of getting a yellow, of landing in a yellow pocket?
0
That's
too.
0.
0. So those are impossible events. You know why? Because they do not belong to the sample space. So they're not enumerated when you're counting the number of possible outcomes in the sample space. All right. So we are just about to now begin some more advanced betting. Okay. So in previous cases, we have talked about, you know, we have talked about getting probabilities for maybe single events or specific numbers. So let's maybe deal with colors, where you're going to be placing a bet on the one that's most likely to occur. That is, where would the ball be most likely to land? Okay, or what's the probability that the ball will land in a particular color? All right. So let us compute these probabilities. What's the next step now? Let me go back to the Word document. Now, we have that the probability of getting a black. Okay, so let me put this here. The probability of getting a black, let's call that B, is 0. 0. What? 0.4736. Okay, and then the probability of getting a red. I'm trying to note this down because we'll be needing these numbers. Probability of getting a red is 0.4736, and the probability of getting a green is what? That was very small. That was 0.0526 because we just had 2 over 38, so 0.0526. So remember that our topic is probabilistic thinking. So let us think about these things. You understand? That's why we're doing a lot of thinking here. So this probability of a black, probability of a red, probability of a green. Okay, so it's quite different from probabilities of individual numbers of the pockets. Now we're just looking at the colors. So we are combining, the number of possible outcomes for each of them. Understand? Now, what happens in a situation where maybe, okay, if you look at these probabilities, okay, for each time a ball is the ball moves, okay, each time the ball is moved, which of these events are most likely to occur? Which of these events, B, R, or G? Which of these events are most likely to occur?
B and R.
Yeah, B and R are most likely to occur, of course, with B and R having equal likelihood because they have the same probabilities. True or false?
True.
So for every spin of a ball, okay, the probability that you get a black and probability that you get a red are the same, and so they are more likely than the event of getting a green. All right. So now we throw the whoever the person is spinning the balls now spins the ball, and in this spin, the ball lands, on zero. Despite that, landing in any of these blacks or any of the reds have far more likelihood to occur. This person spins the ball now and it lands in a zero. Does that make sense? Would that make sense to you after computing the probabilities? Why would there be a scenario uh, um why would there be a scenario where after seeing that the likelihood for getting a green is far less, in fact too less, too small, close to zero, we still had that event happening? I don't know if anyone can tell me their reasoning about it. Because sometimes you see the shock on people's faces when they buy stocks or they make some investments or they carry out some what's it called, under uncertain conditions, and then they are shocked at certain outcomes they have, and then you begin to wonder whether they're expecting, to always have successes all the time. I don't know if this makes sense. Or should I rephrase the question?
Please do.
Because if you lose, anytime you land in a zero, you lose. So you're going to be losing some money or some chips, depending on what you are playing with. Okay, so you are losing here, and then you're wondering why would I lose? The probability of landing in a red is 0.4736. Okay, the probability of landing in a black is 0.4736. In fact, you know the funny thing, we're going to get to a part in this lecture where we'll be adding the probabilities. The combined probabilities is, of landing in either a red or a black is now these two added together, which will give you around 0.94 something, you know. So how come you have 0.94, probability of 0.94, which made you 94% certain that your ball will land in a green, but it's still landing in a green? Okay, you're 94% certain that you land in either a black or a red, but still landed in a green. So why would this happen? Okay, that's because when you check what went wrong, it's because probabilities are only indications of how likely events are, but they are not guarantees. I don't know if that makes sense. So a probabilistic estimate or number or value is only an indication of the strength of the likelihood of the event, not necessarily a guarantee that that event will happen or not happen. So for example, in the case of zero, where you had something very close to zero, it's not zero, so you should already know that that is not a guarantee that that event will not happen. Okay, so no matter how unlikely an event is, as long as it is not impossible, as long as it's not a zero, like as long as the probability is not zero, then it can still happen, even if other events or other possibilities present themselves with strong likelihoods. Okay, that other event can still happen. For example, someone may have created a very sophisticated model of the financial market, maybe cryptocurrencies, and given a very strong, based on so many factors, calculated a probabilistic estimate of what BTC would be, and said, okay, 99%, there's a 99% likelihood that the prices will double in the next 5 days. Okay, but the remaining 0.01%, okay, the price would drop. Probably it would even have to be divided by two, okay, or even worse. Imagine BTC dropping to something maybe below $10,000. People will be in crisis because this is going to be a very huge dip. Okay, it's going to be a very huge dip. But the fact that you had a 0.02 or 0.01 probability that BTC would dip below $10,000 doesn't mean it cannot happen. So don't be too confident in probabilistic estimates. Still ensure that you are taking note of the margin of error to make sure that you can brace up. You know, that's why we talk about risk. You can brace up for that event that has a small likelihood. Still prepare yourself towards it in case it actually happens. All right. So the only thing is that the only reason why, from the frequencies perspective, all these other the probability of getting a red or a black, where they get very strong is, let's say if you can repeat the experiment like 500 times, 1000 times, then most of the times you'll be getting, you know, those very good outcomes. But that's if you have a chance to repeat the experiments, you know, over and over and over and over again, just to get arrive at a certain event. But you know, in a practical scenario like this, you are playing the game. You're not going to be experimenting, you know, to get outcomes and then to get results. You're just going to play the event once. The event happens once, and it can either be in the red or the black, or it can be in the zero. I don't know if that makes sense. Does that make sense? Are you guys with me?
Sorry, sir, I didn't really get that.
I said a lot. So what part did you not get? Hello.
The last part.
Okay. So I was trying to say that um, unless you want to repeat the experiment like over and over and over again, then you know that for sure, you know, most of the time you'll be getting your ball spinning into the red or the black, and far less of the time you'll be getting them spinning into the green. Okay, but in a live game like this, there will be no time to play, you know, make experiments, to carry out experiments and draw your, what's it called. So it's just one of those two cases. Either it lands in a black or a red, or it lands in a green. Okay, so let's do something more. Let's in addition to what we've looked at or done so far, let's now try to see. Okay, before I go into adding these two together, which of course kind of makes sense, we're dealing with probability of getting a black or a red. All right. Um, without adding them together, we can use a different notion to get the probability of having this or this. All right. So, what if we want to? You already know that the total probability of a sample space. Who can tell me the total probability of a sample space? Remember what your sample space is. Your sample space is simply a set of all the possible outcomes. So a set of all the blacks and the reds and the greens, or all the pocket numbers, that's your sample space, and there are 38 elements in that set. So what's the probability of your entire sample space? You can tell me.
1.
It's 1. That's why it's
That's
called,
one.
yes, which is why it's called a possibility space here. So here I say a set of all possible outcomes, also known as possibility space, because the total probability is 1, which means it's a possibility. Okay, everything in that set is makes up an entire possibility, which means it makes up 1. You get? That's because we have certainty that all the outcomes are possible. So summing all the outcomes together gives us 1. All right. Now, if you now want to get, okay, the probability of getting a black or a red without having to um, check, without having to sum these two directly. So you do black or red, probability of B or R. Let me put this back. Okay, probability of a black or red. Let me put all these ones in out of bold. Okay, so what's the probability of getting a black or a red based on just looking at these three probabilities? How do we now get the probability of getting a black or a red? You know what that means? We come back to this formula here. Okay, we know the probability of getting, we know that the probability of getting a black or a red plus the probability of getting a green is what is equal to 1. So the probability of getting a black or a red, okay, is simply equal to 1 minus what? You can tell me.
Minus probability of getting a green.
Minus probability of, yes, getting a green, but
Of
so
getting a green.
yes, you're correct. But before we get there, okay, let us be more precise by saying, I forgot I was not in a Python environment. I was trying to highlight that and put that in brackets. All right. So this is it. The probability of getting a black or a red is simply 1 minus the probability of not getting a black or a red. And the only event where we will not get a black or a red is what? Yes. The only event where we will not get a black or a red is what?
Probability of getting a green.
Is no event, not probability. The only event where we will not get a black or a red is what? You are correct, only that you have used probability instead of event. The only event where we will not get a black or a
Event
red
of getting a green.
is a green, yes. So when we say a black, it's like the event of getting a black. When we say a green, it's like the event of getting a green. So we have to be careful not to, use probability when we are talking only about the event. So this is going to be equal to 1 minus probability of a green. Okay, so if we don't have a black or red event, then we have a green. So the complement of a black or red event is a green. All right, so in that case, we're going to be subtracting 0.0526 from 1, and that will give us, let's go to the next line. So here we're going to be having, what's up on this now? So here we're going to be having 1 minus 0.026, 0.0526, and that's basically what we have here. And that's when you check that, that's like equal to 0.09 0.0974. 0.9 0.9474. Yeah, let's try to align all this. Now what are we doing here? We are trying to combine some events, and as we combine those events, we are looking at the complement case now, where you have what's it called? Let me take a code from this. Okay. I'm so sorry about this. I'm just trying to align the equation. All right. So that gives you the probability. So when we're not looking at the black or red, we're looking at this. Okay. So interestingly, many of us from our interactions tonight, I can see that we have not forgotten our probability. Okay, so it's always good to start with this before we now begin to go into more serious stuff. So just to round up, I want to go into conditional probabilities tonight. So let's try to see. We've talked about complementary events, calculating individual probabilities, complementary events, and so maybe we've also talked about adding probabilities, or no, we've not really talked about adding probabilities. We can add probabilities. So when you have probability of event A or event B, that's an addition, okay, which means you're having a sum of all those events, probability of a sum of the events taking place together. So if you know the probability of getting a B, a black, and the probability of getting a red, okay, then you can find the probability of getting a black or a red simply by adding the two probabilities together. So which means we can simply just say that this guy here, probability of getting a black or a red, is simply equal to the probability of getting a black plus the probability of getting a red, which at the end of the day boils down to this same figure that you have. Okay, so even without going into trying to subtract the complement of that entire event from 1, you still get that result. So we have to understand the various these various approaches, because it's supposed to be equal to, because sometimes it's useful to know the various approaches of arriving at the same answer. We can arrive at the same answer using a variety of approaches, and we have to you have to have those various approaches at your fingertips, because some problems, the way they present themselves, they require you to approach the solution from from a specific perspective, and you might not be used to that one. You might be used to maybe this approach, for example, but now you need to approach it from here. Okay, so sometimes you may not even really know what this one is. Maybe you are not sure of, or you're not aware of what the probability of green is. So this one only works where you have complete information about the probabilities of all 3 events. But where you have only information about just the 2 events, then this is the approach, or this is the formula to use. So we are still dealing with simple formulas here. Let's try to take another bet, okay? So now we're going to do something else, okay? What is the probability? Let us try to check the probability of instead of just landing on maybe specific colors like black or red, what about the probability of the ball landing on a black or even pocket? Okay, what's the probability of the ball landing in a black or even pocket? Already you know that to compute that, we need to know the probability of the ball landing on the black, which means we already know that, okay, this is 18/38. Then we also need to know the probability of the ball landing in an even pocket, and we need to now know the number of even pockets we have here, so that we can know the number of outcomes, the number of possible outcomes for a ball to land in an even pocket. So for an even pocket, okay, how many even pockets would you have between 0 and 38? Actually, let's take out 0. Let's start from 1. From 1 to 38, you have 38 numbers. What is the total number of even numbers that you have between 1 and 38? Who can tell me? Yes, anyone? Um, I hope you guys can still hear me. My mic is unmuted. Can anyone hear me? Or am I talking to myself?
I can hear you, sir.
Okay, so did you get the question?
Yes.
All right, so are you thinking about it, or the question was, we have 38 numbers, 38 pocket numbers apart from 0 and 0, 0. We have 38 pocket numbers. Okay, so what is the total number of even numbers you're going to have between 1 and 38? Or from 1 to 38, what is the total number of even numbers you're going to have here? Because I want to be able to present a use case here, or should I say, I want to present an intuition here that sometimes you can add probabilities together, but it will not always work in all circumstances. Okay, so you need to be able to think of some other approaches. So how many numbers do we have from 1 to 38? How many number of even numbers do we have?
19.
Yeah, it's 19. You simply split 38 into 2. Okay, thankfully, you have an even number of total numbers. So when you split it into 2, you're going to have an equal, it's going to be divided into 2 equal parts. Okay, so the odd numbers, okay, will be 19. The even numbers will be 19. If let's say the number was 37, then there will be more odd numbers than there are even numbers, because you're starting your count from an odd number and you are ending with an odd number. So it's going to be more odd numbers than even numbers. Then if it's 39, also the same thing. Okay, but once you land on an even number, you started from an odd number, you are ending with an even number, then you're going to be having equal number of odd numbers and even numbers, which means you need to just divide the total number by 2. So you're getting 19 for even numbers. All right, so what's the total probability here when we have such a scenario? I mean, what's the probability, sorry, of getting an even number, of getting of an event, the probability of an event of this ball spinning into an even pocket? What's the probability of getting an even? Let's come back to this. Are you guys with me? I'm asking now the probability of getting an even number. Are you sure we have 19? Let me see.
0 point
We have, you said what?
0 point
17.
Someone said 17. We are going to have, sorry, not I made a mistake here. It's not 19 that we're going to have, because the total number of numbers, if you're excluding 0 and 0, 0, the total number of numbers now will be 36. Okay, so which means even numbers now will be 36 divided by 2, which is 18. So we're going to be having 18 here, not 30. I mean, not 19, because we have 36 total numbers, not 38. Sorry about that. So 0 and 0, 0 are out of the way. So we have 18 even numbers. So what's the probability of getting an even number? It's still pretty much the 18 that we had previously. Okay, so which means when you add the two probabilities together, it's still going to give you 0.947. Well, now let's do something. Okay, let's try to count all the holes that are either black or even. Then we divide by the total number of holes and see what that gives us. Because I want us to be very careful that we do not, if you check, the probability of getting a black or a red is this, and obviously probability of getting a black or even, probability of getting a black or let me put it as even. Let me just call this E. Probability of getting a black or even is this. Since the two probabilities are the same, then we still have this number. It's still the same familiar number that we are aware of. Just give me a second, guys. I'm coming. All right. So I was asking this question. Okay. We have these two probabilities are equal. So when you add them, you're still getting the same values. So the probability of getting a black or the probability of getting an even gives you this. I mean, the probability of getting a black or even is this. But what if we now instead count the total number, okay, of holes that are black and holes that are even? That's the total number of holes that are either black or even. We count that, and then we divide by the total number of holes that there are. What do we have?
That's 36 over 38. It's the same value.
Look. We are counting. You have to be very careful here. How do I put this? You're not counting all the black holes and all the even holes. Let me just be sure that I didn't state that wrongly. You're counting holes that are either black or even, which means we want holes that are black but not even, and we want holes that are even but not black. We want to add those two holes together. I don't know if that makes sense. Anyone with me?
Sure, you said black but not even.
Yes, we want to count holes that are black
And
but not even, and holes that are even but not black. That is, we're trying to count
okay,
holes that are either black or even, but not
black and
both.
even.
Yes, not both. Because when we were dealing with the black and
Okay.
the red case, it was quite different. Okay, anything that is black is not red. Anything that is red is not black. But now we have cases where we have some blacks that are evens, we have some evens that are not blacks. So we want to count all the holes that are either black or even in order to find the probability of getting a black or even, for you to know that the probability is not what we've computed here. Let me do something here. So we have this, and so I'm going to put a question mark here just to, okay, that's pause it. I'll put it within the, yeah. So because you have to be very careful, if you just do it this way, you're going to have a problem, because now I want to introduce the idea of mutually exclusive events. Okay, the black and red are mutually exclusive, but black and even are not mutually exclusive. So when we're calculating the event of this or this, if you've been here from the beginning, everything looks like it's simple, but this is where probability now starts getting, very tricky, and you have to be very careful with the notions in order not to get the wrong interpretations. I don't know if that makes sense. Anyone with me? Okay, let's go back to the roulette board. So, you know what? Let us count, okay, all the holes that are either black or even. So let's start from holes that are black but not even. Holes that are black but not even. All right. Holes that are black but not even. So okay, let's count. Let me just do the counting so that you can wrap up this session very quickly. So we have I'll count clockwise. So one, I'll start from here. One, holes that are black but not
8.
even. Two, three. Okay, Miriam says eight. 4, 5, 6, 6, 7, 8, and 9. The holes that are black but not even are 9 in number.
No, they are
No,
8. You
they are
counted 8.
I
8 is
counted.
easy.
They are 8.
Okay, I counted. Okay, I'll go again.
8.
Just I'll go again just to make sure I'm not. Um, I need to verify this again. So 1, 2, not 2, 3, 4, 5, 6, 7, 8. Okay, that's very good. So we have 8 here. Now let's check holes that are even. But not black. So you can note down 8 holes that are black but not even. Note it down. Then let's check holes that are even but not black. So I'll start from 5. That are even. Okay, sorry, even but not black. So 1, 2, 3, 4, 5, 6, 7, 8. So again here we have what we have 8. Who counted that and also got 8?
Yes, 8.
Okay. Now, hold on a second. I want to be sure I'm not misinterpreting this. I think we might have made a little error in interpretation here. So we want to get holes that are black, that are either black, okay, that are either black or even. Just a second. Let me be sure that. Okay, guys. We have made a mistake in interpretation here. So the interpretation here is get me holes that are either black or even. Of course, that's the statement. But interpretation is this. Okay, we have a set of all the numbers that are black, or yeah, all the numbers that are black. Let's have that set. I hope you're following me. Are you following me? Then let's have the set of all the numbers that are even. Okay. Now, when we count, when we are counting, we are going to count. Let's try to now join the two sets together. Any number that occurs twice, we count it as 1. Does that make sense? Because if we have 8 and we have 8 in the second case, it's not enough. It's not what we're talking about. It's not black or even. Okay, you know what? Let's make this more practical. I'm going to leave this slideshow. So I'll come out of this slideshow. So let's come back here, and then I'm going to do this side by side so that we can count while working with it. All right. So let's check the set of all black events. You can be writing this down as well so that we don't get confused. So let's create a set of all black pockets. Let me reduce this so that set of black pockets. pockets. So we'll be counting from here. I think I should put this one, this particular one in this view so that it gets bigger. All right. This. We're gonna have a problem there. So set of all black pockets. So we'll be looking at all the pockets that are black. Okay. So let's bring out all the numbers where you have black pockets. So just to make it easy for me to pull out those numbers, I want someone to read out the numbers. The numbers you have on the roulette wheel that are black. Just read out all the numbers, whether it is odd or even. Just read it out for me. Let's go.
2,
Okay.
35, 4, 33, 6, 31, 8, 29, 10, 13, 24, 15, 22, 17, 20, 11, 26, and 28.
Okay, so we should be able to verify that we have 18 numbers here. So we have this 6, 9, 12, 15, 18. So that's very good. So we have 18 numbers there. Now let's check a set of even pockets. Okay. So the set of even pockets now, let's continue that count. So all even numbers, whether they are black or white, apart from 0 and 0, 0, which are green. So let's run the count again.
So 14.
Sorry, the other time when you
4.
counted, did you count clockwise? How did you count? Where did you start from? Okay,
I
starting from 2
counted
here.
anti-clockwise.
You counted like this, right?
Yes.
Starting from 2.
Yes.
Okay, I want to kind of it will not be easy to order the whole thing. To be more stressed, so probably we should not go that line. Let's just continue. Okay, so 2, 14, yes. I can see
4.
4 here. Okay.
16.
Of course, if we order, if
16.
we order the whole thing, we're supposed to be getting. We should just do 2, 4, 6, 8, 10, 12. But let's just follow this order like this. All right, continue.
6. 18. 8. 12. 10. 36.
36,
24.
4,
34. 22. 32. 20. 30. 26. And 28.
all right, very good. Thank you very much. So now um, we have this set. So since we followed anti-clockwise, we can now merge what's it called? The two sets. What we're going to be doing here is a notion of union of a set. So when we do union, we try to unite the two sets, okay, just picking out individual occurrences in both sets. So if a number occurs here and occurs here, okay, we only have it in that set once. Does that make sense? let me take this to the next line. All right, so what we're going to be having here is set of black or even. That's the next thing we're going to be doing. I don't know if you guys are with me. How many of us are still here? We'll just try to round up with this. So set of set of black or even. So let's now merge these two. Let me remove all these other ones. And let me increase this. All right, are we ready? So we'll just combine these numbers. Okay, 2, 2, 35, 14, 4. I don't know if that makes sense. So starting from here, are we ready? Miriam, are you ready?
Yes, sir.
Do you understand the agenda right now?
Yes, we are picking one where the number occurs twice.
No, we're not picking where the number occurs twice. We are merging the two together. Okay.
That's
Well,
everything.
yeah, we're merging everything together, black or even. The only difference is that 4 here that occurred together here, we only write 4 once. Okay, not twice. That's why the first time you did that check, you did 18 plus 18, it was 36. The second time when we did 8 plus 8, it was 16, it was still less. Do you know why? Because we now checked, okay, we made the two events mutually exclusive. So anywhere I have even here, take it away. Anywhere I have a black here, take it away. All right. But now instead of mutual exclusive, we want to do union of the two sets. You understand? We want to do a union of the two sets so that we are not having to take away anything or all that. We just unite the two sets by checking out the numbers that occur in all the cells, in all the sets, I mean. So 2 occurs here, we write 2. Of course, it occurs 2 times, we only write it once. 35 occurs here, we write it. 4 occurs here, it occurs here, we write 4. I don't know if that makes sense now.
Yes, that's what I was asking. That where the number occurs twice, we only pick one.
Okay. I thought what you were saying was that we're trying to check only where the number occurs twice. Sorry, I misunderstood you.
Okay.
Yeah. So this is 31. This is the next thing is what 18, right? So please just be
18,
looking at this so that I'm sure I'm not making a
8,
mistake. 6, 31, 18, 8.
8,
Okay. 29,
29, 12,
12,
10,
10,
13, 36, 24, 15, 34, 22, 17, 32, 20, 11, 30, 26, and 28.
All right. So this is what we have now. Okay. You can now see that it's longer. It's not 16 now. So if we count all the elements here, what do we have? It's 4,
Excuse me, why did we not add 14?
14. It's 14 here.
Yes, check a big
We didn't add
number,
14.
even person.
Oh,
Yes.
yeah. Thank you
Yes.
very much for the observation. That would have been a problem. Would have gotten a wrong result. All right. Thank you very much. So we have 4 here. Let's just count. Sorry about that. 4, 8, 12, 16, 20, 24, 25. Let us end with 4, 8, 12, 16, 20, 24. We're missing a number here. So it should be 26 numbers. So we have 2, 2, 35, 14, 4, 33, 16. We don't have 16 here. So we miss that. So So I will need to reduce this set so that it fits into the line. All right. So we have 26 numbers. Okay. Therefore, the probability of getting a black or even is what? You see, it's no longer that probability we computed earlier. That probability would have given us an error. It's now the total number of possible outcomes. This is actually the number of possible outcomes. A black or an event or an even event has 26 possible outcomes, and not the this thing we're looking at earlier, not the this one is when you check 18 plus 18, that's 36. So 36 divided by 38 is this. If you also check mutual exclusive, which is 8 plus 8, 16. 16 divided by 36, it gives you a smaller number. The actual number is 26 divided by 38. Sorry. Divided by 38. I hope that makes sense. And if you check that, that should be
Sorry, why are we not dividing by 36? Because our sample space is 36
no, the
in
sample
total.
space is 38. Remember that we are still going to be including this 0 and 0, 0. So
Okay.
the total sample space is still 38. Except that the numbers now, because it starts from 1, the numbers terminate at 36. And then this 0 is the 37th pocket, the 0, 0 is the 38th pocket. So we have a sample space of 38 possible outcomes totally. So this should give you 26 divided by 38, 0.6842. So that's the probability of getting a black or even. So you have to be careful here. This is the notion of union of a set. I don't want to go too much into details about set theory. If not, we'll just do some Venn diagrams to make it easy to visualize. But I'm sure you guys can just do that as an exercise. Just try to maybe use Venn diagrams to look at it. If we do it as only places where you have black, that is events of black that are not even and events of even that are not black, then we have two mutually exclusive events. Okay, because now we are trying to exclude black from even and exclude even from black. Then if we do it combined, that is all the blacks and all the evens, some pockets will repeat themselves. So what we're having there, what would you call such a situation? Okay, can't remember the exact picture for that. So you're going to be having a problem too, because you will be you'll be having duplicates, and so your computations will not be correct, because you can't have for example an event and getting into 6 twice. Okay, there's only one outcome for a 6, but 6 occurs here and occurs here in these two sets. So if you have 6 6, it means you're saying that there are two possible outcomes to get a 6. Is this reasonable? Are there two possible outcomes to get a 6? No. So even though a 6 is a black and a 6 is a even, there's only one possible outcome to drop on a 6. And so we have to truncate any duplications that there are in order to get the actual results. So there's also the notion of intersection. Intersection is now where we have sorry, did anyone say something? So there's the situation where we now have, okay, let us speak out. I think I should talk on that before
Please
we
check
round up.
your chat. Check the chat.
Okay, let me see. Okay. So sorry guys. Yeah, 12 a.m. for you. So sorry about that. All right. You know what? I don't want to. I want to move into conditional probabilities tomorrow. So let me just round up with this. But with what we've done so far, I think um, we really understand this. So I'll just try to round up. But anyone who now wants to maybe go to sleep or something can just can you can leave the meeting now. So the rest of the recording will not be so much. So I should just quickly wrap up with intersection problems. So sorry for the time taken. It's just that we have a lot of these things to cover. Unless we can schedule sessions in the daytime. So I don't know. Maybe we would discuss that in a group chat. So it would be useful if you can have sessions in the daytime. Um, if that's possible, then we can work on that so that we look at all these things. Saturday is also going to be a long day. We'll be looking at morning and evening sessions. All right, so let me just quickly wrap this up. But for those of us who want to leave the meeting now, we can, and then we can catch up with the recording later. It's not so much I'll be dealing with here now. So we are trying to work out the probability of when dealing with the case of working out the probability of the ball landing in a black or red pocket, we're dealing with two separate events. Okay, so the two events, a black event is not a red event. They don't coincide. So there are two separate events. Okay, if the ball landing in a black pocket and the ball landing in a red pocket are two different events, there's no coincidence between them. So we call these events mutually exclusive events. So let me write that as B and R are mutually exclusive. So I posted something earlier today, which I think I should talk about mutually exclusive events. About mutually exclusive events, because sometimes, except you, there are those who strongly understand the details when we talk like this, when we use terms like this. But sometimes for others, it can be a little bit abstract. So if you want to draw this home, okay, if we really want to explain this to make it very clear, when we say two events are mutually exclusive, it's like saying you have two events that we are talking about here, okay, that should occur. But unlike in the case of a black or even pocket, these two sets have this set of black pockets and set of even pockets. You can see that they have so many things in common, so many outcomes in common. So they are not mutually exclusive. They have a number of outcomes in common. But when we draw out a set of black pockets and a set of red pockets and we check all the elements in common, we can find one thing that is clear. We can find that all the elements, that the elements in black or the elements in red, we can find that they have no elements in common, so they're exclusive. Okay. Now we use the term mutual because we are saying that these two sets, okay, there's one thing that they have in common. That is, there's one thing that they have mutually. There's one thing these two sets have in common. It is the fact that they have nothing in common. You understand? So a set of black pockets and a set of red pockets, they have one thing in common. That is, they have one mutual, mutual kind of interest, or there's something mutual about the two of them. So when I say mutual, it's like common interests, something common that we can identify, that we are identified by. So when you look at us, you can see something common with us. In the case of a red event and a black event, that one thing they have in common is the fact that they have nothing in common. That is the fact that they are exclusive. So exclusive means we don't have anything in common, or we don't have some things in common. But mutually, or mutual means this is the one thing we have in common that we don't have anything in common. So the one thing we have in common, mutual, is that we have nothing in common, exclusive. So they are mutually exclusive. But when you check the two sets and you can see that they have some numbers in common, then they're not mutually exclusive events. Okay, uh, they have intersections. So we can use intersections to also work around our calculations. We can check which numbers intersect, calculate the number of intersections that we have in that set, and also from there now come back to compute the probability of um, either of the events taking place. So B and R are mutually exclusive events because, let me take note of that, because so they are mutually exclusive events because the only thing they have in common is that they have nothing in common. That's very important. So it is impossible for the ball to land in a pocket that is both black and red. It's impossible. You don't have a pocket that's both black and red, but you have a pocket that's both black and even. You have a number of pockets like that. So let us try to calculate. Let's try to work out in these two sets of even pockets and odd pockets. I should reduce this total font size. So in this scenario now, let us now try to work out the intersections. Okay, where do we have intersections and what is the number of intersections? So they are not mutually exclusive because the ball could land in a pocket that is both black and even. So there's intersections. So what we should do now is get the intersections. So to find the probability at an intersection, or the probability of getting a black or to find the probability of getting a black pocket and the probability of getting an even number, is more or less like to find a joint, not a joint probability, yes, probability of either way. We can work from the intersection. So let's do that. Let's compute now. We already have the probability of having a black, which is, let me note all those things down. Probability of having a black sorry about that. So we already know that probability of getting a black is what? 0.4736. And then we know that the probability of getting an even what's the probability of getting an even? Did we check that? We can use this. It's still the same. It's still the same 0.4736 because it's 18 elements. So if you add the two together, you would be getting how do I put this? If you add the two together, it's like you are counting, or you are getting a probability of, this is looking bigger. You're getting a probability of having some numbers, some outcomes occurring twice when they should occur once. So instead of adding the two together to arrive at this, we add the two together and then subtract the intersection from them. So let's look at the probability of the intersection. So the probability of B intersects, let me take this off. Probability of B intersects E. Okay, we need to now check all the numbers that occurred in both sets. So we have 4. Okay, we have 4, we have 6, we have 8. That's 3 numbers. We have 10, 4. We have 24, that's 5. We have 22, that's 6. We have 20, that's 7. We have 26, that's 8. And we have 28, that's 9. Alright. Are you sure it's 9 we have here? We have 2, 1. We have 4, 2. We have 6, 3. We have 8, 4. We have 10, 5. We have 24, 6. We have 22, 7. We have 28. We have 26, 9. We have 28, 10. So we have 10 numbers there. Okay, so the probability of B intersect E is 10 divided by 36, and that would give you, when you divide 10 by 36, let me see, that's like 5/18, so that gives you
Sorry, sir, 36 or
0.277.
38?
Sorry, 38. Oh, thank you very much. 38. So you can see that 36 is already getting into my head. So you have 0.263, 2632, 0.2632. That doesn't look very good. So this is it. So this is the intersection. Okay. Now we want to arrive at this. Okay. Starting from these probabilities: probability of getting a B, probability of getting an E, and then the probability of intersection. We want to ensure that we remove the intersection. By removing the intersection, what are we achieving? Can anyone tell me? By trying to subtract the intersection from the total of, from the sum of this probability of B and probability of E, what are we really achieving? What we are really trying to achieve here when we
That's
subtract the... Okay, go ahead, Miriam.
I don't know, probability of not having an intersection.
Ah, I would say I agree, but probability of not having an intersection, we already have an intersection here, so we don't need to compute the probability of not having an intersection, because clearly an intersection has occurred. When we check the two sets, there's an intersection. So we don't need to check a probability of not having an intersection, because there's an intersection. You get? So what we are really doing here is that when we pull out an intersection, we're simply pulling out, it's like you join the two sets together. Let's join the two sets. The probability of, those two sets, that is, join them as they are with the duplicates, gives you this probability plus this probability. But when we pull out the intersections, like, we're not pulling out the duplicates. We're not pulling out all the, like, for example, when we check the intersection of the two sets, we're going to have 4, 6, 8, 10. Okay, from 2, 4, 6, 8, 10, 24, 22, 20. Do you get? We are having this, and that set we're going to be having for the intersection is not a duplicate set. It's just one of those, one of each of the duplicate values is what we are bringing out, more or less. So by subtracting the intersection, is like we are pulling out, the extra values. The second time that each of the values occur, we are pulling out those extra. I don't know if that makes sense. That's basically what we're trying to do here. We're trying to pull out from the sum of these probabilities the extra that should not be there, because each of those events, each pocket has an outcome, only one possible outcome. The event of landing in the pocket is just it's just one outcome. The total number of possible outcomes to land in a particular pocket is just one. So we cannot have two possible outcomes for a specific pocket. Does that make sense? Marian, did you get that? Hello. All right. Yeah. Did
No,
you get what I was trying to explain here?
no, sir.
Okay. You know what? Why not let's pull out the intersections? Okay. So let's from here. Maybe I should how do I do this? Let me create a new page. Let me enter a new page. Sorry. So starting from here, I'm going to paste that again. But the goal here is, instead of set of black or even pockets, okay, the set of intersection That is where the values co-occurred. So the set of intersection, or let me just say the intersection, because the intersection itself is a set. So the intersection of both pockets. So instead of having set of black or even pockets, let's check the intersection. So I'll be removing this. So tell me the numbers that occurred twice or more. Starting from 2. I mean, they occurred twice, not there are no more occurrences, just all the duplicates occurred just twice.
Two.
So we have 2, we have 4, we have 6, we have
6, 8,
8, we have 10,
10,
we have 24,
24,
um,
22, 20, 26, and 28.
so how many numbers in total do we have here? We have 1, 2,
That's
3,
10.
4, 5, 6, 7, 8, 9, 10. So now
Six.
look at this. Look at this. If I take these numbers and I say, okay, from that total set that we previously had, let me bring it back. Let me bring this one back. From the entire combined set, no, not this, this one. Okay, from this entire combined set, although we do not have duplicate values here, but let's assume that all these other values were duplicated. That's those further occurring values, more occurring values were duplicated. Do you get? Now, if I now say, okay, all the numbers we have here, okay, let me remove exactly these numbers from this set, or from not this. This is not the set I need. I need the entire set where you have all these 18 plus all these 18, 36 numbers. So if I now say, okay, this particular ones, just this specific 8 numbers, or I mean 10 numbers, let me pull them out from the set. You get? So I will now leave the other one that occurs again, like by the time I pull out 2, I will leave the remainder 2. By the time I pull out 4, I leave the remainder 4. I don't know if that makes sense. By pulling out all these numbers, okay, when you are done from that set of 38 numbers that you have, when you join these two together, this is what you are left with, this particular line here. Does that make sense? My set of black or even numbers is simply this set plus this set minus this set. Does that make sense?
Okay, yes. Yes.
Yeah, so let me just indicate that. So I would say that is set of black or even numbers is equal to set of black pockets, it should be even pockets, set of black pockets plus set of even pockets minus what? Minus intersection of black and even pockets. This is what we have. I hope that makes sense now.
Yes, sir.
All right. So let me just to create space. Let me take this off, so that will be available on the next page, on the previous page. So that's basically what we are dealing with here. It's probably not intended that way. So this is what you have here. Now, which means if you want to now find the probability of black or even pockets, okay, how do you write the formula? You know, without thinking too much, all you just need to do is just give me a second, let me bring this out. So the probability of a black or even pocket, okay, is simply this probability here represents this, is it not? So what is the probability that represents this set of black pockets? We write it here. It's simply the probability probability of black plus probability of what? Of even minus what? Probability of black intersect even. So let me put the intersect symbol. This is how we arrived at that initial. This is how we now arrive at the probability of black or E, which actually gave us this figure. This figure, you obtain this figure by counting all these things, trying to check the set and counting this one. But very fast, you just simply, what's the probability of black, of getting a black, compute it. What's the probability of getting an even, you compute it. Then you subtract the probability of the intersection from that sum. And that's simply now, this what you're doing, simply doing here is you are simply removing duplicates. Let's use data science language. You understand? You are simply just removing duplicates in the data. That's basically what you're doing. All right. So once you get this, you can now get a result. So let's now, let's now get the values. So probability of a black is, already we know that to be 0.4736, and then this one is 0.2632. So this, okay, no, 0.4736, 4736. Are we sure we are? Yes, 4736 plus 0.4736 minus this. This is what you have here. And by the time you check the, you further sum them, you're going to be having, what do you have there? Let me see. 0.4736. 0.9472, then minus 0.2632 gives us 0.684. So we have 0.684 as a result here. And that's pretty much everything that we are doing here. So I think we can stop here for now. We'll continue with the notion of conditional probability from tomorrow. And then from there, I think after conditional probability, we can just really would have enough time to, because conditional probability is just for us to look at the reverse. Yeah, we'll look at the probabilities given certain additional information, and then we'll look at the reverse of those conditional probabilities and explore Bayes' theorem for arriving at the results. So with that, we should be good to go. So we are going to be stopping here for now. I'm so sorry for the time that has been taking. All right. So that brings us to the end of. Actually, there's still a couple of things that we need to calculate on the probabilities, but we've looked at pretty much a lot of the ideas. So maybe what I would just do next is to do a small pre-recording and to continue, some of those details. So, but for the other details were pretty much done, so we can stop here for now. So yes, let us now try to. So sorry for taking your time tonight.
Thank you.
Yes, you're welcome. If you have any questions, just because of time, you can always send the questions maybe on the group chat, so that I can treat each question.
Night, sir.
Yeah, although if you want to ask them here, you can still ask. I'm still going to be, I'm still very much active. I'll continue the recording for this session. All right, so I guess now it's just the pre-recording. So the next notion we want to look at, okay, is the notion of we've talked about intersection. I've been able to arrive at the intersection by trying to figure out what each probability is, so many probabilities, and then getting the probability of the intersection. So with that, I mean, when we carry out these steps, we are getting the probability of two events occurring which are not mutually exclusive, which in this case, the two events we're actually looking at here is like um, the event of getting a black and the event of or the event of the probability of getting a black or getting an even. Okay, so it's those probabilities now that we are computing. I mean, this probability now that we're computing, and so we check the individual probabilities of black and even, add them together, and then subtract this from this. Because if we just add this together, we're going to be making a blunder. The blunder being that we are going to be having some outcomes in these events occurring twice, and each pocket, okay, you can only have one possible outcome for each pocket. All right, you can only have one possible outcome. So you only talk about two or more outcomes when you are now combining with other details like, okay, this or this or that, so on and so forth. So you may wonder, why is it then that when we are dealing with mutually exclusive events, we just do P of B plus P of E? Why are they different? Okay, why are they different? When we're dealing with mutually exclusive events, we just simply add the two probabilities. Okay, so you might be wondering, why are they that way? That's because if you have two mutually exclusive events, the probability of getting A and B, of getting A and B is actually 0. Okay, so your intersection is AND. So when we say probability of B intersect, is like saying probability of B and E, which means everywhere B occurred and E occurred at the same time. Okay, so when you have mutually exclusive events, the probability of getting let's say let's say B and red, that's B and R. Okay, the probability of getting them, of getting B and R, that is the probability of B intersection R, is 0. Why? Because there's no intersection. The two events do not occur together. All right. So with that, we simply it's simply like saying P of B plus P of R minus 0. So this formula is more of general. It's actually pretty much general. You can still use this for, it's not very different from computing the probability of two mutually exclusive events. You can still use this formula. The only thing is that you're going to be having 0 here. Okay. But for events that are not mutually exclusive, you'll not be having 0 here. The reason being that um, you have events that you have duplicates. Okay, so those duplicates are those that fall at the intersection. We have to pull at the intersection. We have to subtract the intersection. That's very important. Okay, so before we proceed, let us quickly take a look at some of the calculations we've done. Let's summarize the calculations we've already done so far. So we start with this. We already identified. We use this formula where the probability of an event A is simply the total number of possible outcomes for that event divided by the total number of possible outcomes in that sample space. So once you can identify the number of outcomes you can have for that particular event, you divide it by the total number of possible outcomes that can occur in the entire sample space. Now, if you take the probability of that event A and add it to the probability of the complement of the event, that is all other events other than the event A, when you add these two probabilities together, you get 1. So the probability of A and the probability of A prime is simply the probability of your entire sample space. So you can work your way around. You can work your way to reverse this equation to arrive at either probability of A prime or probability of A. So depending on the information you have and what you're trying to compute, you can arrive at any of the two probabilities simply by subtracting the other probability by from 1. Now when you check the probability of B, that is the probability that the event is black, that is the probability that the ball spins into the black pocket. Okay, we already computed that the probability is this number, which is 18 divided by 38. And since there are also 18 pockets, 18 red pockets, the probability is also the same. Then the probability of getting a green is very small because there are just two pockets. So we are now looked at mutually exclusive events, black and red, which do not occur together. So when you check the probability of getting either a black or a red, probability of a black event or a red event is simply the addition of the two probabilities. So simply add the probability of getting a black and the probability of getting a red. That gives you the probability of getting a black or red. Okay, and of course the other approach to computing that is simply that the probability of getting a black or red, we obtain that result or we obtain that result by subtracting the probability of a green from total probability space. And that's because you just have three types of events. You have a blue, you have a black, you have a red, and you have a green. So based on color, we just have three types of events, and all these three are mutually exclusive. So when you add all these mutually exclusive events together, they give you one. Okay, so you want either black or red. Simply subtract, the probability of a green from the entire sample space, the probability of the entire sample space, and that gives you this. But what if you're dealing with events where two outcomes, uh, events where events that share outcomes? For example, the event of a black and the event of an even number. So some black pockets are actually even numbers. Okay, some even numbers are black pockets. So when you're dealing with this kind of situation, we identify that we extend the formula for this by subtracting the probability of the intersection between those two events, because these two events will be sharing common elements. Okay, so when you check the total number of possible outcomes for these two events, you find that outcomes repeat themselves. So we take away those um, the extra outcomes. So where there are duplicates, we just take away the extra, we leave one of the outcomes. For example, if two occurs twice, we take away one of the twos, we leave the other one. So that's the reason we're taking away this. Okay, now if you take a look, you realize that it's still pretty much the same with this, or should I say, you can compute this probability simply with this formula. Okay, it's just for you to realize that the probability of an intersection for mutually exclusive events is 0. So by the time you apply this formula on a mutually exclusive event, okay, it reduces to this formula because this is 0, so it just solely reduces to this. Okay, so take note that the probability of you know of um, of an intersection of two events is simply probability of that event and the other one. So blue and red. Okay, so when we say the probability of B intersects R, this is simply saying the probability of the B events and the red events occurring together. Okay, so we know that the blue and the red events are mutually exclusive, so the result is 0. So the probability of a B and the R is 0. They can't occur simultaneously. Okay, you can't have shared outcomes between them because we don't have any pockets that are both blue and red. Now the probability of a black event and an even event, the probability that an event is black or an event is even, that is actually possible. That could happen because you have some black pockets that are even, and so the probability of this, okay, is this result that we computed earlier. And this is also, remember that the symbol here is the probability of this and this, so that gives you this. Now the probability of B union R is simply the probability of B or R. Okay, so the probability of B or R, which means either B or R. So we are more or less adding these probabilities, and in the case of mutually exclusive events, we just simply add the probabilities of B plus the probabilities of R, and it gives us this. But when you have intersecting events, we just don't stop at adding, because we're going to be having repeated outcomes in the entire set of the joint events. So instead, we would have to, after adding, we have to subtract the intersection so as to remove the duplicate values. So in the language of data science, you're simply trying to remove the duplicate values here. So the probability of a B, that is the probability that the event is black or the event is even, is actually less, in this case, compared to the probability that the event is black or the event is red. That is the probability that you have outcome that is black, an outcome that is black, or that's an outcome that's an outcome in the black pocket. So moving on, we have talked about mutually exclusive events and all this, but let us look into some of these types of events in detail, where you're having um, outcomes of two different outcomes of two different events. Okay, how can we differentiate between these various types of outcomes, and what do they really mean? So let's take a look at various types of events, um, events where you're considering maybe two at a time. So we have mutually exclusive events, we have intersecting events, and we have exhaustive events. So let's look at them one after the other. So when you talk about mutually exclusive events, these are events, okay, that do not intersect. These are events where the outcomes are not shared. The outcomes cannot occur simultaneously. So the events B and R are mutually exclusive because only one of the two can occur. You can't have both occurring together or simultaneously. Only one of these two can occur for any given trial. So it's impossible for the ball to spin in a black pocket that is also a red pocket. It has to be either a black pocket or a red pocket. So you can't have an event where the outcome is shared for these two. It's not possible. So this is a mutually exclusive event. So basically, when you look at this diagram, it's telling you that you have all the possible outcomes for black and all the possible outcomes for red, and none of those outcomes coincide. Okay, so when you take a look at this, it means it's simply saying that we do not share outcomes here. All right, so like I explained or I talked about earlier, when we say mutually exclusive, okay, exclusive because they do not share outcomes. So when you check all the possible outcomes that you can have, you check that set, write out all the possible outcomes. We do the same thing for already. You discover that you don't have similar values. Okay, so because they do not share possible outcomes, their outcomes are entirely exclusive. They're not sharing. Okay, they do not share anything in common. Okay, so they are exclusive. The outcomes are entirely exclusive. All right, now it is mutual because now there's something interesting about these two events. Okay, you can find out that the one thing that connects the two events, or the one thing that they the one thing in common that they actually share is the fact that they do not share anything. So they share one thing in common, mutual, the fact that they do not share anything in common, exclusive. So if you think about it, that's really how you come about these two words, mutually exclusive. Actually, they're just exclusive events, really. They're just exclusive, so they don't share anything in common. But we say mutually exclusive because we want to introduce the notion that yes, they share this one thing in common, the fact that they do not share outcomes in common. So they don't share outcomes in common, so exclusive, but they share that characteristic in common, so mutual. All right, mutual for the fact that they share a particular characteristic or a certain property in common, exclusive for the fact that they do not share outcomes in common. So what they share in common is not outcomes. What they share in common is a characteristic that they do not share outcomes in common. I hope that makes sense. Now, let's talk about intersecting events, which are quite different from mutually exclusive events. In fact, it's quite the opposite, okay, or maybe almost the opposite. Now, intersecting events are like events where there's an intersection clearly, so which means they share elements, okay, so they have outcomes that coincide because the two events, it's possible for the two events to occur simultaneously. So the ball can land in a pocket that is both black and even, right? So where you have outcomes, where you have possibilities for, um, where you have possibilities for, you know, events. I mean, for um, outcome to land in the black pockets and in the even pockets, right? Such possibilities are shared. Now, if you draw the sets, if you pull out the set individually for black and pull out the set of possible outcomes individually for the even event, right, you realize that you're going to be seeing, values in black, some values in black, or some elements in black. You'll be seeing those elements in the even set. All right. So if you combine those sets together, all right, you'll be having duplicate values. We need to eliminate those duplicate values, which is why in the previous formula we introduced um, the notion of subtracting the intersection just to remove the extra. Now, events like this are also called mutually inclusive. Why mutually inclusive? Inclusive because they share outcomes. All right, so they have that in common. They share outcomes mutually because, of course, they have that characteristic in common. All right, so um, what they have in common, when we say mutually, what they have in common in this case is a characteristic. And when we say inclusive, what they have in common in this case, all right, is the outcomes. So they have outcomes in common, inclusive. Then they have that characteristic in common, mutual. They have that characteristic that they have outcomes in common. All right, so I hope that's not too tricky. Okay, so the one thing they have in common, mutual, is the fact that they have outcomes in common, inclusive. All right, so moving on to exhaustive events, we've talked about exclusive and intersecting events, and we looked at we looked at the fact that intersecting events are mutually inclusive, and then the very first one is mutually exclusive. All right, but there's to be something, another notion we can take a look at or interpret when dealing with combination of events like this. So we have the notion of exhaustive events. Okay, so when we talk about exhaustive events, what we're really saying here is that we have two events that are occurring such that all the possible outcomes you can have in this entire sample space actually exists within those two events. So these events A and B are said to be exhaustive events if you cannot find possible outcomes in a sample space outside of A and B, which means all the elements, all the possible outcomes you would have in this entire sample space, you would actually find them in A and B. Okay, so if you have 38 possible outcomes, okay, you would have all those 38 outcomes within this entire sample space. I mean, you would have those 38 outcomes, okay, within the union of these two events. So what that simply means is that A or B exhausts all possibilities. That is, the union of A or B simply exhausts all the possibilities. It captures all the possible outcomes that you can have in that sample space. So the probability of this union is actually 1. Okay, the probability of A union B is actually 1. That is, the probability of all the outcomes occurring in this A and B is just equivalent to the probability of all the outcomes occurring in the entire sample space, and that's equal to 1. Okay, so when you add up all the probabilities together, you're going to be having 1. Okay, so they exhaust all the possibilities, therefore they're called exhaustive events. All right, let's move on to exclusive versus exhaustive events. So it can be quite tricky, and you have to be careful about the difference. Although, yeah, there's a serious difference between exclusive and exhaustive events. But let's try to now look at them. So if two events are exclusive, of course, you already know that there's no intersection between them. So the probability of A intersect B is 0, which means you can't have A and B occurring together. So the probability of A and B is 0. Okay, so A and B, which means they can't occur together, so there's no intersection. All right, so that's 0. Now, when the two events, when you check the two events and the probability of A union B, as I mentioned earlier, is 1, if the probability of A union B is equal to 1, it simply means you are having the equivalent of the probability of the entire sample space, and therefore, those events are said to be exhaustive. So the probability of A union B is equal to 1. So they are called exhaustive events. But there's a possibility for you to have an exclusive and exhaustive event at the same time. Okay, so I mean, you can have exclusive events which are also exhaustive events, or exhaustive events which are also inclusive events. So if A and A prime cannot have common elements, of course we already know that they are exclusive, they can't have common elements. But this A and A prime can also make up the entire possibility space, so they are also exhaustive. That is what I mean by that is, let us ignore this second diagram for a moment and focus on this. So we already know that these two events are exclusive. All right, exclusive. I don't think this diagram should even be here, because A prime cannot intersect with A. You can't have an intersection of A prime and A. Okay, so let's remove that. So we just need just this diagram. All right. Now you already know that A and A prime cannot coincide, because A prime is everything outside A, so you can't have an intersection here. All right, so they can't have common elements. All right, so let's say you have this set of A and A prime, which means A and everything outside A. Obviously the two sets are exhaustive because they make up the entire possibility space, which means everything you have in that sample space exists within these two elements. Okay, so even if it's not A and A prime per se, even if it's just A and B or A and whatever event, of course that event now becomes the prime of A, because everything that is not within A is going to be found inside this particular set. All right, inside this particular set of events. So clearly, when you have two events that are exclusive, but the events are also exhaustive, which means they capture all the possible outcomes in the entire sample space, then obviously each event is a complement of the other one. So A is a complement of A prime is a complement of A, clearly. Okay, because all the elements that you will not have in A would fall inside A prime, not outside there will never be a single element falling outside of these two. Okay, so all the elements you don't have in A prime will fall into this, and so it's called exhaustive. So you can have if two events that are actually exclusive and at the same time exhaustive. So you can have uh, uh, exhaustively exclusive events or exclusively exhaustive events. Okay, so in the previous case, where we noted these differences, um, you have exclusive events that are not exhaustive and exhaustive events that are not exclusive. So this is not exclusive, this is not exhaustive. Okay, so the only way this will be exhaustive if this is a complement of this, which means these two, all the outcomes you have in the two make up the entire sample space. All right, so this is not this other diagram here is not exhaustive. I mean, it's not exclusive, but it's exhaustive. But now you have a scenario where you can now have the two together exclusively exhaustively, and that brings us to the end of this lecture on calculating probabilities. So next we'll be looking at conditional probabilities, where we'll now introduce some notions from Bayesian statistics. We'll be looking at the frequency case now, where we are carrying out experiments by counting the number of events. So it's counting we are doing frequentist statistics. So now we'll be proceeding uh, to the notions of degrees of beliefs, quantifying uncertainties based on degrees of belief, updating degrees of belief based on available information, and we'll see how probability can be computed when we have access to information and how we can update those probabilities as new information become available. So the probabilities that we are going to be computing in this case are conditioned on how much information that is available to us. Okay, therefore conditional probabilities. See you in the next lecture.